After 3 is. All right, so now we're going to start talking about combinational circuits, okay? And we actually got a little bit of a jump start on this because of the work you were doing for circuit number 1, right? So we're going to peek into it, but now we're going to go into some nice detailed discussions of the ins and outs of how to read, write, design, optimize, all those kinds of good things on combinational circuits. Of course, you already looked at the table of contents of your text anyway, so you know what's coming up, right? No surprise. I can't fool you, right? I just can't fool you guys. You're at the top of it. Good. Okay, so starting at the top, because we want to make sure we do understand some of these terms that maybe you didn't read thoroughly or something. So we want to make sure we understand all the terms, okay? So starting off with a combinational circuit, we say that a combinational circuit is some, you can think of this as kind of a black box type of thing, where you have this box, this component, that has m number of inputs and n number of outputs. Okay, and since we're talking about a Boolean logic circuit, then of course they're all Boolean inputs and outputs. All right, so inside of this circuit, there's a bunch of switching functions, and the exact switching functions will be determined by whatever it is we want this particular circuit to do. Okay, so the complexity, we can design these boxes, these combinational circuits, to do a lot of very complex things, or they could be some very simple things. Or, as is most cases, somewhere in between, right? So what we want to do with these combinational circuit boxes is basically, we want to apply the scientific principle to it, right? Big box, bunch of hard, complex stuff inside of it. In order for us to solve it, we're going to break it down into smaller boxes that we can work with, we can describe, or optimize, or whatever. So we're going to take that circuit and we're going to decompose it down into smaller, what we call blocks. That's an official term that we'll start using now, blocks. Okay? Likewise, we'll take the function associated with that component, or sets of components, decompose those down into the smaller blocks, and we'll keep repeating that process, drilling down deeper into smaller blocks, drilling down deeper into yet smaller blocks, until we get the smallest box that we can possibly get, which is called our primitive block. The primitive block is the smallest block that we can describe, that we will create to describe the function of the components that we decompose this larger, much more complex circuit from. Okay, to get a good visual picture and something we can talk to visually, we have an example looking at what's called an 9-input parity tree. All right, so jumping right into this parity tree here, you can see at the top is that 9-input combinational circuit. Up at the very top has 9 inputs, 0 through 8, has 1 output, C0. Okay? And we give it a name, and the name is typically something that we can associate with whatever the functionality is for this particular circuit. In this case here, we called it an odd function, 9-input odd function. This is going to select our odd parity components. Okay? So we give it a name that we can associate with this function or capability. And then we want to drill down and say, okay, let's decompose this down a little bit further from this one big box. And what we're saying is that what we really have is this collection of 4 3-input, 1-output boxes, so we're circuits. I have these 4 subcircuits in 2 levels, right? So I need 4, and I've arranged them in 2 levels. So what I'm doing is each of them have 3 inputs. So I have the first 3 taken 0 through 8. There's my 9 inputs, right? And they're going to select their odd function, and it's going to feed it into the second level input odd function circuit, which will take those 3 inputs and generate 1 output from there. All right, so that's how we can get from there to there. We simply say, oh, I've got these 9 inputs, I've got 1 output. I'm going to design it this way. So this still isn't our primitive block, is it? It's still this notional thing. We have this functional description for a name that we've given it to it. We don't know how to implement this thing yet. So let's take a look at just one of them. And each one is identical to each other, except that we're going to hardwire different inputs to them and hardwire their outputs, right? So let's take a look at the function. Well, it turns out that I can implement this 3-input odd function generator by simply using two, what's this symbol name? What's this gate?
OR.
Exclusive OR, or XOR. Okay, so I can implement it with two XORs, A0, A1, A2, A3, A4, A5, A6, A7, A8, right? So I can implement this using A0 and A1 into this XOR, and then take its output and XOR it with the third output, third input to generate the singular output. Okay, so I can implement each one of these this way. Well, it turns out the XORs are still not the most primitive thing. Now, there are some chip manufacturers, you can go out there today, you can get a collection of XORs, you can work with them as primitives. But let's take this down just a step lower and say, if I wanted to build, or you wanted to build an XOR, how could you do it? Well, you could do it with this collection of 4 NAND gates. Okay? So notice 2 inputs, 1 output, 2 inputs, 1 output. What I'm going to do is take 1 input, feed it into level 1. So notice this is a 3-level diagram here, right? So we have 3 levels. So I can take the input for the first 2, right? Because each one of these XORs is 2. So I'm just taking one of these, has 2 inputs, feed it into this NAND gate, whose output then goes to the other side of these 2 NAND gates, who then feed that NAND gate, and that will, if you build your logic tree, show you that it, in fact, is an exclusive OR, meaning only this or this, but never both 1, never both 0. So one has to be a 1, the other one has to be a 0 for an exclusive OR, right? And that's what these 4 NAND gates, 2 input NAND gates will do for you. So that is our primitive block. Okay, that's our primitive block. So now you've got a lot of information here, right? So if you needed to implement this thing, you're saying, hey, I'm working with NAND gates here, you can quickly determine how many NAND gates you need, right? How many?
8.
No, more than that.
More than that.
Right? I'm going to have 4
32?
for each one of these. 32, exactly. How'd you calculate that?
Started
chips.
from the bottom and then just doubled and then
4 times 2
times 4
times 4.
times 4 again.
No, just once.
Oh, sorry.
Yeah. There.
Yeah, I just got 2, right. So 4 of these times 2, so 2 of these are going to each have 4. And then I'm going to, in each of those 4 circuits up there, have 8, right? So that would be times 4. Yeah.
So like in real life, it's like a bigger chip. It goes smaller and smaller. Is that what it's representing?
More abstract, less abstract, pretty firm, and I may actually have these chips that I can go buy, but I said, no, we don't have them. We got to make them still primitive. Okay? So this is the least abstract. That's somewhere between the most abstract and the least abstract. But they're very useful. These levels of abstraction are very useful because one of the things we're going to sort of fast forwarding here to another slide I'm going to have a little bit later. One of the things that we're going to want to do is we want to think about reuse, right? So if I build these different levels of abstraction and then I further down the road need another one of these circuits, well, I've already built one. I can go grab it again, just like you did in assignment 1, where you built your MUX and then you put it into a library. And then you can reuse that library in circuit diagrams without having to rebuild that MUX every single time, right? That's the goal here as well. As primitive, we have these gates, ands, ors, nands, and nors. Right? The most primitive thing we have are those gates. How can we then make very sophisticated things and complex things using these packages and do it in a timely manner to create these levels of abstraction. Just very similar to what you're doing in code. When you were writing code for your previous classes, you were creating functions, you were creating data structures and variables, and then you reused them. That was one of the purposes of building them, so you could reuse them. And that's what we're doing here as well with the circuits. Our good friends over in the EE and CE department are just as smart as we are. Maybe. But we'll give them the benefit of the doubt. So they like to do reuse as well, okay? So that's what we're talking about. Does that make sense? Oh, yep, I did talk about reuse. Here we go. So for reuse, of course, pencil and paper is very, very useful, but it's also time consuming, just like writing code on paper is useful, or writing it on these whiteboards is useful because then you can collaborate with somebody. But at some point, instead of being on paper or doing a screenshot of, doing a picture of the whiteboard work, you need to get it into a file that the compiler can read. Or in the case of these types of diagrams where I'm working with circuits, I need to get it into the right kind of computer-aided design. CAD stands for computer-aided design, if you're not familiar with that. Computer-aided design, which is what your LogicWorks is. It is a CAD tool. Okay, so you can create circuit diagrams in there. You can create libraries of these circuit diagrams and these circuits that you create in there, and you build from those components, or the most primitive components. You have that collection of things that your CAD tools can use. Okay, this gives you reuse. This gives you speed and productivity, right? Which is one of the things you want to do. The other thing I should point out is that not only are you getting the speed, but you're also getting the reliability. Because one of the things you did when you were building your bugs for assignment number 1 was that you tested it thoroughly. You made sure that you mainly built the truth table, and you made sure that when you implemented, or at least most of you did, matched the truth table, right? So you validated it. Okay, and that's one of the very important concept to bring with you in this discussion, because as you check something into a library, you create a library of these specific circuits that you build, and you validate each of these circuits. When you go to reuse it, you know it's going to work correctly because you've already validated it. You're not putting it into the library until you have done that. Once it's in the library, you know it will work correctly because you validated it. Okay, so the speed of reuse includes things like trust, right? You now trust this particular component, this particular circuit, because you built it, you validated it, and then you checked it into the library. Okay? I think I said most of those things. Yeah. Oh, the other thing I did say here, so in our particular tool, LogicWorks, we actually have several different ways we can share the information from this tool. You've been looking at the library, and you actually turned in your CLF file, which contained the library of this MUX that you created, which when you decompose it, and double-click on it, decompose it in the circuit diagram, we'll show you the exact details of how it was implemented. But there's other ways as well. You can share the circuit diagram itself. Yeah, you can do that. But once we start getting more complex, we start designing very complex systems, even those become cumbersome to work with. I mean, yeah, you'll still probably want to show libraries. But when you're doing the design work, it becomes very tedious to work with design trade-offs in the tool using point and click, drag and stuff, because those circuit diagrams become very, very large, very quickly. Okay, so we have some other tools, and you've heard some reference to those when we're introducing the tool, LogicWorks, and when you were starting to work with it. And that is, there's these two languages that it supports, VHDL and Verilog. Okay, so those are descriptive languages, like software languages are, like C or C++ or Java, or insert your favorite programming language here. It's like a different programming language for the CAD world, electronics CAD world, okay? So we have these two languages that this tool and many other CAD tools for circuit design use. And that gives you some interoperability, which is a good thing, because sometimes tools go out of business, or at least the manufacturer stops supporting it, and somebody else picks it up, or somebody comes up with a much more powerful version and you abandon the other one, so you go to a more powerful one, or lots of different reasons why you might go between different vendors' products. So one of the things you like is interoperability. You would like for your code, if you will, that you wrote in Verilog or VHDL, to be able to work in LogicWorks, but you would also want to take it over to another CAD tool when you start working on that project, or if they upgraded the CAD tool, and not have to redo all of that stuff again. Okay, so that's one of the things that we're going to look at a little bit down the road, but not too much further down the road, is these particular types of language tools that the CAD tools provide us. Okay? All right, now, great. CAD tools, we know a little bit about them. We've got the concepts of circuits down to primitive blocks. Got it. Well, great. If I wanted to design something, I'm using the tool, or I'm using the conceptualization of the tool called Whiteboard, whatever I'm doing, what's the best way to start working on the problem, solving this problem? Do I start with the very top requirement, build a bus? Or do I start at the very bottom? Well, in the beginning, I had an OR gate. And then I put two OR gates together for 3 inputs, 1 output. Then I put 2 AND gates together, 4 inputs and 1 output. So you start designing components bottoms up if you want to. You can start designing your system tops down. But the reality is we typically kind of do both at the same time. Or what we might do is we might start off with top-level design and create a bunch of subsystems and then send those off to different parts of our team to work on. There's lots of different ways you can approach the problem. Not unlike big software systems, where you might start your design top-down. What's my top-level requirement for this software project? Or the bottom-up. Well, I've got an integer. I've got a character array of, oh, say 24. Maybe I have another character array of, say, 8. Put them together, and I've got an address for a street. You know, you can start doing it that way as well. Create a bunch of fundamental data type, a little more slightly complex data types, call it an address or a phone book entry or something like that. You can do both. It's kind of similar to the top-down, bottom-up approach that we're talking about here with the hardware. So the hardware, not unlike the software, we can do the same type of thing. But we have these trade-offs. The one thing that's kind of maybe helpful to think about when you're talking about top-down versus bottom-up is the top-down approach is saying, hey, what is this thing that we're supposed to be running here? What's it going to do? And the bottom-up is the how, right? So you can see, oh, yeah, I've got these 2 things here, and so on. Right? So that's the whole idea, is that you can take the 2 different approaches. We typically use some combination of it because it's sort of human nature to want to go ahead and start doing stuff. Like, I'm sure more than half of you, at some point, one of your classes, when you got assignment number 1 or assignment number 5, you just started writing code without doing a big analysis of what is this thing going to do? What is it the instructor's asking for? I don't know. I've only got 2 weeks to do this. Let's start working, right? Only to find out that after 4 days of hard slaving labor over the keyboard, you discovered that, oh, I didn't understand the requirement altogether that well. Well, I understand better now, so I'll make this work. And you go back and rewrite code. Okay? Rewriting code, of course, is a whole lot easier than putting hardware components together and finding out that some don't work or do what you want them to do, which is another reason why these CAD tools are so important, because we can work through those issues using the CAD tool before we actually commit hardware to the prototype or the first article design, and end up having to throw a bunch of that stuff away because we weren't paying attention too carefully, or we were in a hurry to start building something. Okay, which is kind of human nature, but it gets expensive. Right? So what about this thing that we keep hearing about called chips, integrated circuits? What is that? Well, basically, they're a package of these things. Circuits that you created, this mux that you created. Okay? You can hand that to a hardware developer or hardware manufacturer and say, here's a circuit, I want a chip that does this. And they can translate your circuit drawing or your VHDL or your Verilog into an actual component, an actual integrated circuit, which is typically some sort of semiconductor thing using little tiny pins on them, and wafer, and then they're actually layered. I should have put a picture right here of them. They're actually layered, so that that's fair. See if I can make a drawing of one here like this. And then silver on the other side. And it's got some numbers up here, IC 45 or something like that. And a manufacturer's name, made in Malaysia, all that good stuff. You'll see on there. Okay, so this is a very simple package or a very simple integrated circuit. So it might be something like 4 muxes put into one package or something simple like that. By the way, just so you know, one of the things that absolutely drives your good friends over in the computer engineering department and Double E school that are focused on building these things is reducing the numbers of pins that it takes for any one of these packages. That is a big deal to them because every one of these pins costs a lot. When I say cost, there's a lot of things, a lot of factors that go into that cost. There's the actual cost of human hours to research, develop that component, and seeing how you can optimize it so that multiple primitives can co-share any one of these pins and how they can manage that. But the idea is that each one of these is expensive because not only is it the design, but it's also the manufacturing. This pin costs a lot more than these little ands and ors and nands and nor gates that they're building. So those things are really, 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 really inexpensive. These cost like 100 times a collection of maybe 10 of them or 100 of them. Okay, so these pins are very expensive. The other thing that happens is that when you go to assemble this pin, assemble this chip onto a board, it takes time and resources to get that onto the board, soldered correctly and tested correctly, and then you're going to run power through here, so it's generating heat, which then has to be managed and is blown away as well. Okay, so pins are very expensive for them, and they will spend a lot of effort, a lot of time trying to reduce the numbers of pins on any one of these integrated chips. Okay? So when you hear them talk about pins, it's a big deal. Okay? So you distract me. Where was I going with this? Oh, yeah, so we have these chips, and of course you've probably seen, I know you've seen because like in one of my early slides, I showed you what a CPU would look like, right? And it's got a whole bunch of these pins all over this thing, on all four sides of it. All these pins. Okay, lots and lots and lots of pins, and we just talked about how they like to reduce them, so you're saying, wow, those things must have a lot of work behind them, and they do. Yes, it's a big deal. Okay, so this mux package might have 4 muxes in it, or 2 muxes. CPU is going to have a whole bunch of stuff inside of it. Okay, so one of the things that we need to do is we need to be able to differentiate the complexity of these chips from amongst each other, right? So we do actually have terms, and I'll put the common ones, the 4 most common ones up here for you. So we have the small scale integrated chip here, all the way up to this very large scale integrated chip here. Okay, and then we have a couple levels in between, which are very common in a lot of these platforms that you see. Okay, so we have these terms because they're going to help the design team for the chips, as well as the design team for those who are going to use them on any circuit board for whatever it is that they're trying to build. Okay, we give them these terms just so to help them understand and prepare for the complexity involved with designing, building, and testing a board that's going to use 1 or more of these versus 8 or 10 of these, okay, or 1 of these and 100 of these, whatever it is. Having these terms is helpful for estimation and planning. Okay, so that's one of the reasons why we use these terms, and it's important to understand them and use them correctly. Some more terms. We love terms, right? We talked about terms before, so here's some more terms. Fan in. Fan in. Okay, we've seen fan in. We just didn't recognize it at the time. Every time we were looking at an AND gate or an OR gate, and I have like 2 inputs and 1 output, that's an example of a fan in. I'm taking 2 in and reducing it to 1 out. And that's what a fan in will do, is it will reduce input to output. Okay, it might not be 2 to 1, it might be 4 to 1, or it might be 4 to 2, or it might be 32 to 2, or 32 to 4. It could be some combination that's appropriate for that particular integrated circuit. That's what we're talking about when we say fan in. Fan out, just the, well, it's not just the opposite because it's more, actually, that was the next slide. Fan out is talking about how you can take and connect multiple chips to a single output. Okay, so in this example here, I have a NAND gate. Actually, I have 4 NAND, well, 1 through N NAND gates plus 1, right? So I went through N plus 1 inverters, not NAND gates, but inverters. And so this inverter here, I'm taking its output and I'm sending its output to the input of these additional inverters downstream from it. Now notice in this drawing here, I show that as a hard circle where I connect those two. You've probably seen, hopefully you've seen, some drawings like this. Let me make that a little bit shorter. Like this, where I might have one input going to 2 different gates, so I have this fan out that we're talking about here. But I also might have, one do like this, something like this. And I have this funny shape here, which is telling you that these 2 lines here are not electrically connected. Okay, they're physical space. It appears that their physical space in 2-dimensional anyway is intersecting, but they're not intersecting electrically. In other words, there'd be another layer or something preventing those 2 from actually touching. So that shows some separation. Now, some CAD tools don't show that because they have other ways of communicating the same or similar information. Okay, so this dot here indicates that they are connected electrically. That means that they are not. Okay, so in the case of the fan out, you of course would have this hard circle to show you this fan out is electrically connected, the output of the one to these other inputs. Yes.
I don't really get what's going on. Like, why would you invert it twice?
Why would I do what?
Why would you invert it twice?
Oh.
I don't really get what's going on.
It could be, it's not supposed to really make much sense other than to show you this fan out type of thing. I mean, I could have had OR gates, NAND gates, other things here. You're right, inverting doesn't seem to make much sense. Although there are some times when we do, because I might have this connected to two of these, then I might skip two, and then two more, and then skip two, and so on, and then have the outputs of these connected to some other types of gates.
Well, then how does it relate to the diagram you showed over there?
So what I showed you here, again, is the connection is this dark circle. The whole point of this fan-out discussion in this slide here is to show you that these are electrically connected. This is not electrically connected to, if I call this A and this B, A and B are not electrically connected. So even though I'm running this line up here, and if I'm using circles, I could even get away with just showing it like this, and I still would say those two, A and B, are not electrically connected. But A is electrically connected with this input and this input. Just like that inverter is electrically connected to 1, 2, all the way through N. So we're just trying to show you in a two-dimensional drawing that we can have things appear to be connected, but they're not. And things that are definitely connected. Does that make
So
sense?
fan out being the idea, like both A and B are fanned out because B is, I guess, forks.
Well, actually, B is fanned out as well, but it's fanned out to these two pins.
All right.
Yeah. So, because I had that dot there, showing it electrically connected to those two gates. Okay, so fan in, fan out. Logic levels. 1 and 0. We're going to talk about those a little bit, in a little bit more detail a little bit later. Noise margins, likewise, we're going to talk about some noise margins. I've got some good discussion coming up on that. You've got some good reading on this, both logic levels and noise margins, because if you go back to our early discussion in chapter 1, we're calling these 1s and 0s, but they're levels of voltages. And it takes time for levels of voltages to change. Okay, so we're going to be concerned about that. So we're going to come back and take a look at these in more detail on some subsequent slides. Cost per gate. This is the measure of the contribution of the inputs. Propagation delay is the time it takes for things to move between levels. Okay, so signals moving between levels will have some propagation delay because it takes time for these components to switch. It takes time for voltage to rise, time for voltage to drop, and it takes time for it to move from one component to another. Power dissipation. This is the big one for our good friends in CBW departments because they are very, very concerned with power because these chips are going to generate heat. And it's consuming power, and we know it's consuming power because it's giving off heat. Right? So they are very much concerned with that. And that's what's allowing our gates to operate and switch. Remember, because really that's what these gates are. They're switching, right? They're switching levels of voltages. And depending upon whether they go above a threshold or down, drop from a threshold, it changes from 1 to 0 or 0 to 1. Right? All right, a little bit more detail then on propagation delay. Okay, so propagation delay, like I said, the time it takes to change on the input side of our gates. Okay, so some component downstream changed. It takes time for it to move to the next component at the next level. That's our propagation delay. Okay, usually this is a really simplification because we don't usually switch right at 50%. We switch at other percentage values, but sure, we'll say 50% for argument's sake, it's just not a hard value. Okay, the delay is usually measured at 50% point, kind of, sort of. But they'll always be consistent. We say, oh, we're switching at 40, it'll be 40. And then we have these terms high to low and low to high. Okay? So high to low, total propagation, TP, HL, high to low, and low to high, TP, LH. Okay, are the two different ways that we have of measuring our signal, our propagation signal. Okay? Diagrams. They are so helpful, aren't they? Okay, so notice what I have going on here. I have the input of some component, okay, at some low value here, some very low voltage value here. And what happened was, this is our sort of our starting state. Okay, we came in, things were happening, but we started looking at this particular gate, this snapshot in time, whatever time value for nanoseconds we currently are. At this time, that's where we're starting for this analysis. Okay, and at some point, the input to this gate started rising. Okay, the output of the gate isn't going to change until, in this case here, some value is reached, and it looks like it might be full high voltage. Oh, if you think that's the high voltage. Once it reaches full voltage here, then it switches, and that is, it starts to drop the value on its output. It is not instantaneous, just as the input did not rise instantaneously. A voltage was applied from the chip feeding this particular chip. Voltage was applied, it started rising. It takes time to rise. It's consuming power, giving off heat, because there's some resistance in the material itself to change. So that increased voltage is going to make it change. It's going to go high. At some point, it switches. At that point, it's then got enough voltage to cause it to determine that what it's supposed to do on its output side, because this looks like an inverter, doesn't it? This output side is to drop the resultant voltage that it's sending to the component out and downstream from it. And it does so more rapidly than it changed on the input side, which is not uncommon. Okay? And then once it gets to its low voltage level, it'll just stay there. Then at some point, the input voltage to this inverter changed, right? And then the same happens just in the reverse. So we're talking about the propagation delay back to low to high, high to low. We talk about those in two different terms because it's typically two different values, because in one case, going from low to high, it's resisting that change because it has to build up that capacitive charge and be able to overcome the zero state that it was in. But dropping it low to high with a component connected to the other side means you've dropped applying voltage to it. The other side is still consuming it, so it's going to drop a lot faster because it's being consumed, right? So it's not having to change anything until it drops down to zero. At that point, it's overcoming that resistance, and it's going to happen much faster. So that's why we're concerned with low to high and high to low, because they're two different values that will affect our total propagation time. Delays. All right, so that's the propagation. Now we have these other delays. We have this first one we call the transport delay, which is the change in output in response to the input. Right? So we saw that here where we saw, hey, at some point we hit the threshold, and then it's going to take time for it to change the value on the output side, and off it goes. Okay, so transport delay is pretty straightforward. But then there's this thing called an inertial delay that we're also concerned with. In the case of inertial delay, it's very much like our transport delay, except that the output is going to be resistive because of the capacity change, just like we talked about before, okay? And one of the reasons why that's so important, the reason why they designed these chips to have this capacitive effect is because a lot of these circuits have noise in them. None of our circuits, a lot of these circuits, all circuits have noise. Some have more noise than others, okay? And one of the things that we want to do is we want these gates to act as a filter against these noise signals that happen, okay? So these noise signals happen. We want these gates to have this inertial delay so that it can filter through these random spikes of power that happen on these lines. There's lots of different reasons. Because one of the common ones is that these components, and even like on our VLSI packages, these pins on these components are very, very, very close to each other. So electrically, you can have some field induction going on, okay? And there's ways that they manage that too, so they can minimize the amount of induction that's going on. But sometimes if you have some rapidly changing value on one pin, it could create a momentary spike. And if your gates are designed to be able to handle going all the way through those spikes, then you don't have to add additional circuitry just to do that for you. So one of the things that we do take into calculation and we actually put into the design is the ability to have some inertial delay, because that's going to be, if we design it correctly, enough for us to be able to filter through most of the noise that will be on these boards. Okay, so we have this notion of rejection time that we introduced with our inertial delay, and that is what I'm talking about when I say we have this filtering action going on. That would be this particular component filtering through or rejecting that change in signal because it's too momentary in nature. Okay, so here's an example of it. Okay, where I might have two inputs, A and B. Okay, A switches, then B switches. Now, we have several different delays here that we've represented. One is an instantaneous no delay. In an ideal world, well, seemingly an ideal world, in the perfect world, right, where there is no noise and everything switches the same nanosecond and things are good, okay, that would be our no delay scenario here. Okay, and it's useful because we can use this to help talk about why these other delays are important, such as the transport delay and inertial delay. Okay, so let's see what happens. A switches, B switches, with no delay, we instantly switch. Okay, what we are talking about in this particular diagram here, what these lines here are showing you, are the two delays. There's the propagation delay, and then there's the rejection time. Okay, so the rejection time is the black line here, the short one, that's our rejection time. This is the filter that we were just talking about. And then we have the propagation delay, the time it takes for the signal to go through the component to the input of the next chip, and that's when it switches to 1. That's when we say it switches to 1. Okay, so transport delay, inertial delay are same here. And what we're saying is that nothing tried to switch at this time here, so they were able to both cleanly switch. Okay? Then what happens is A drops to 0 at this point here. Okay, and then we have those two clocks going on. Now at this point here, they don't switch until it's fully propagated. In this case, they both fully switch. Okay, now look what happens. B momentarily goes up to 1 and then drops back down. Okay, so we have the events in a non-delay scenario where it goes ahead, it goes to 1 and 0, but it doesn't propagate. It doesn't propagate And what happens is, the next event, which is where it goes back to 1, but A drops to 0 happens. And now, in our transport delay, this here switches because that time of that circuit there. However, it hasn't overcome inertia. So the inertial delay has prevented this from switching. So it's going to miss that. It would treat that little time. Just notice how short that time is? Okay, if we say that's how much time we need to design this particular set of circuits to reject noise, okay, and that's the width of a noise, a little bit less than 1 nanosecond. Okay, so if I have some voltage which caused one or the other to switch within 1 nanosecond, I want to reject it. And that's exactly what we're showing here with these filters. So what I get here under the inertial delay, saying, yeah, transport delay, it's going to get fooled some of the time, but our inertial delay is going to smooth over it. So in fact, what we get are just those cases where they both switched and stayed to that value long enough to overcome any noise spikes that might have been occurring in the system. Yes?
So the inertial delay graph is the one that you want from
Yes.
the. Okay.
Exactly. Yeah, that's what we're talking about. That's what we're trying to show here is to say, what I really have is the condition where A and B both stayed 1 long enough for, and stayed 1, right, long enough for this to really be declared a 1. So we rejected a noise spike there. Likewise, we were able to reject this lack of noise, which is itself is noise, right? If I suddenly just drop voltage for some reason and it comes back a nanosecond later, I want to just smooth over that. I want to filter over that. And that's what the inertial delay is going to enable us to do. Does it make sense? Wasn't obvious when you're first looking at circuit diagrams, right? That was going on. That's one of the reasons why I spent a little extra time on chapter 1 going over some of the physics behind these components, so that when we get to this discussion here, hopefully it makes more sense to you. To us, it's a world of ones and zeros, so we can use code to write these things, make this computer do what we want it to do, but the computer is still all about hardware, which is an analog world of reality. Okay, so that makes sense? Let's then talk about, yes?
What would you use transport delay for? If you want the inertial delay as like the output.
So the transport delay is a real property. So one of the questions I have is transport delay by itself enough? And we can see here that by itself it is not enough if we decide that I need to be able to handle spikes of this duration. Okay? So that's why we put that up here, is to say it's a real physical property, but it's not good enough for a lot of the types of noise that we see. Great question. Other questions for Juan Cost? Cost, okay. Cost in an integrated circuit. Cost is proportional to the chip area occupied by the gates. We what we use to calculate. Okay. Reason being is that the size of the actual individual elements within the gate are also fixed known things. Of course, when I say fixed known, they keep making them smaller and smaller and smaller over time. But typically, they're transistors. Right? Transistors and resistors are the main fundamental components used to make these gates work. Okay, so we talk about transistors a lot. There's resistors in there too. They have to be in there for switching. But the transistors, the number of transistors is the big thing that they will count. When I say they, of course, the W's and CEs that design these chip sets are counting numbers of transistors. And you may have heard that. You know, we're up to a billion transistors inside of one VLSI package now. Why is that a big deal? Because that is the most fundamental block of significance within the integrated chip itself that we're looking at. Yes, there are resistors and capacitors built in there too, but those are supportive of the transistors. The transistors are the devices that actually switch. So that's the thing that they will count as the most primitive or most fundamental electronic component inside of these chips. Okay? And then the wiring and the timing. What's really cool too is the timing of these things. Okay, it's the distance between one transistor and another, the leg on one transistor and another. So if you have an old can type of transistor, for example, and it typically has 3 legs to it, and it has 3 legs to it, and then you want to switch it, or you want to connect it to another transistor. Maybe let's go somewhere here. One of the things that you're doing now, where we are with the design, is that the length of these connections, which really means the length from here to here, because the pins are a fixed size too. Okay, the length, it takes a certain amount of time for electricity to move from this point to this point. And so they're at the point now where they're developing the timing based upon the length of these connections. Okay, and they're dealing with timing that way now. If you look at some of the more recent high-performance computers, what we used to call supercomputers, we now refer to them, of course, as high-performance computers, and there's different kinds of them. But they're even on large scale. That is, if I wanted to connect a CPU to a memory bank, those are now also being timed just by the length of the wire between the CPU and the memory bank itself. And then they're adjusting these lengths to get the timing just right and balanced between all the other subsystem components as well. So we're down to the point where we're really looking at these links as the factor for controlling the timing of signal propagation, time of propagation between component A and B, or subsystem of CPU and membrane 0. Okay, so that's why it's so important to have this transistor count, this understanding that the most fundamental thing of importance that we count in our integrated circuit package is the transistor, and that's going to then determine, what kind of density it is of numbers of transistors per square inch or square nanometer or whatever value they want to use. That'll tell them the density of the chipset for that particular chip. That will also be part of the cost. Okay, so when we talk about proportional number and size, that's really what we're doing. We're saying, losing by the caps. We're really talking about how many of these transistors do I have in any package. There'll be bigger transistors in this package than they will be in this one, without a doubt. Okay, so counting the cost, I want to know the number of transistors. How do we know that? By the numbers of them, which can be calculated from the size. Okay? Typically, we ignore pinouts when we start talking about the cost of these components, although, like I mentioned earlier, it's a very big deal when they start talking about them electrically, because they will be generating heat and they do take time to connect. So you just understand, why is this important to me? Last I checked, I got accepted in a computer science program. We are here talking about hardware. Yeah, we're talking about hardware. We said we're going to talk about hardware all semester. So stick with me. You gotta need to understand this part here, because recall, leading up to exam number 1, we were concerned with optimization of the design of these systems, right? In this case here, now we're talking about circuits and what we call when we decompose the circuits down into something else, we have a name for that. Blocks? Blocks. There we go. So now we're concerned with circuits and blocks. We're down to our primitive block, right? And therefore, we're going to be concerned with optimization of these as well. In order to understand optimization, we have to understand we do want to reduce the numbers of transistors, but how does that equate to ANDs, NANDs, NORs, XORs, and higher level things? Well, that's what we need to take a look at. That's what we need to pay attention to. So in the case, so in this example here, I have a NAND gate, right? The NAND gate G, and it says has 20 standard nodes. I output has this delay, which is what 0.45 nanoseconds. And then we say it has normalized cost of 2.0. Okay, that's always important to normalize these costs because different manufacturers may have their way of calculating costs. And it's supposed to be standardized, but it's not. It's a big world with everybody trying to come up with their marketing genius strategy on how to convince people that their gates and transistors are better than anybody else's gates and transistors. So one of the things you have to worry about when you're doing design and optimization is trying to get through that. So we'll have to normalize our costs. That means we're going to come up with our standardized cost estimate. And we will use things like our ratios, our dimensional ratios to numbers of transistors, and we use that uniformly across all of the components, regardless of who made them and what spin they may have put on their description of these packages. Don't you love the word spin, right? It's just a fancy word for lie, distort, right? So yeah, anyway. So we're gonna get past that because we're scientists. We don't distort and lie about things. We deal with facts, right? So we come up with a standardized definition of what our cost is and how to measure it. Numbers of transistors per square millimeter or whatever it is that we want to use. So we use that, we say, oh, okay, so now what I have is I have a gate that takes these kinds of loads, it takes this much propagation delay, my formula then says it has a value of 2.0. Okay, now let's say I have a buffer. It comes in at a cost of 1.5. Okay, the NAND gate is driving it with this 20 standard loads, and therefore giving us a total delay of 0.33 nanoseconds. All right, so this is the problem set up. I've got my NAND gate G, I've got my buffer H. These are their two cost values, and now I have NAND feed buffer. Okay, so the question then comes up: which of these three cases that you see up here should be added for when I'm adding this buffer? I'm going to take the cost of the circuit and say it cannot exceed 2.5, delay can't exceed 0.4, or that the delay of the circuit itself must be 0.4 nanoseconds and cost less is 3. Right? What do you think? Yes?
I think the buffer fulfills all of those.
All of them. It's the right answer. Excellent. Because, yeah, go ahead.
Doesn't number 3 cover all of them?
It does.
So there's number 3.
But these two describe how you got there, right?
Number 3 is more strict than number 1 for the delay. Right?
Well, you can.
No, it's less strict.
I can still create a cost function that doesn't exceed 2.5 that doesn't meet this performance. Right. So yes, it is more explicit, but it might reduce some of the ones that meet number 1, some of the designs that meet number 1. So when you're looking at defining what your requirements are, this is one of the reasons why I like you reading this and thinking about it just a little bit, because when you start determining your requirements, you can simply say, okay, I just want the cost to be 2.5 or less. You need to take and realize that you've got all three things, all three parameters, that are involved. And if you don't care about the timing, right, then they might not meet the timing, but they'll still meet when they do their optimization to meet your requirements of 2.5, get you there without being truly optimized. So, questions? It might be 2.5 is all you care about. You don't care about being the 0.4 nanosecond high-end requirement. If that's true, then that's fine, because you might get a less expensive solution. It just might take a little bit slower, but that's okay for your particular circuit that you're designing. Who knows? I don't know. Depends on the situation that you're designing. And that's the whole idea about bringing up this discussion of trade-offs. Because when you're doing optimization, it is possible to optimize yourself out of a competitive market. Right? You can come up with the optimal solution, but superconductivity, it's expensive, it's probably not the tool that you want to use in your solution design, right? So you can go with a little slower propagation path, that's fine. Or maybe you do need superconductivity just to get to that value because it's really critical for this particular component. If it is, so stated, stand by for the cost. Right? Okay, perfect. So we'll get us started and we'll finish up on design procedures. All right, so I have some steps here. That you should be thinking about. So, okay, I got it, I understand its cost, propagation, these different delays, and these different types of chips, and how to come up with cost. Okay, I got all that stuff. How do I do my design? How do I approach the problem? I got top down, I got bottom up, what should I do? Right? Well, typically, when we're doing design, well, we're going to start off with a specification. We're going to say, what is this thing supposed to do? What do you want it to do? In this case, it is a circuit. Oh, by the way, for those of you who might have taken software engineering or thinking about taking a software engineering class, you'll notice some similarities here between what we're talking about designing circuits versus designing software. Not too far different. Okay, there are some distinct differences, but not by much. Not as much as you might think. Starting off with the specification, that's everything. Now when I say starting off means referring back to it, because it's really easy as you're going through and doing further detailed analysis, or you're doing further decomposition of your problems into smaller problems that you can then build a solution for, to get lost and stray from the real requirements. So it's a really good thing to periodically go back and make sure that what you're doing is traceable back to your system specification requirements. Okay? All right, so start off with specification for your circuit. In this case here, we're talking about a circuit, so you say, I want this circuit to be MUX, okay, with 4 inputs, generating 2 outputs, and it has an enable gate. Okay, that's what I want to do. Start off with your specification for your circuit. Then you want to go what we call the formulation phase here, which is really saying, in the case of circuits, what's the truth table? What's the K-map? Okay, what does this thing look like from a Boolean equation perspective? Can I define exactly what this is supposed to do on any given input? Right? And what resultant output? Then I can go into my optimization phase, okay? Do 2-level, do multi-level, do cost, all those different types of things. Drawing out my circuit diagram so that I can take a look at it might not be the final one, but at least start looking at the problem so I can start doing the optimization either from looking at my K-maps or looking at combining circuits, okay? Then there's this other step that sometimes people forget about and overlook. That is technology mapping. Did I design a sub-circuit that looks just like something else that already sits in the library? I probably should pay attention to that for 2 reasons. One really important reason, and it's how we started off tonight's discussion. Remember what that was?
Trust it.
Trust it, exactly. It's been validated. Right? In the library, it's validated, it's trusted. So even though you might have drawn something here, I would jump to the one in the library because it's trusted, it's validated, we know it works. Then the final step is verification, which the more trusted components I use, the better the validation is going to be. My verification is going to be, okay? more reliable. But it's gonna be also less work. Right? If I'm using a whole bunch of validated things, then all I have to do is worry about how I connected them up and how they interoperate with each other. I know that they're going to implement their logic correctly, so I don't have to do those, but I do have to worry about how they're connected, so taking into account propagation delays and all the other things that we were just talking about tonight. And this is probably a good place to stop because this will take a little bit more than 5 minutes to get through. So we'll pick up on this on Wednesday.